How you doing, Year 10s? Welcome to another video. This is Unit 4, how can we control the speed of reactions? And in this video, we look at how do those reactions occur. Let's get straight to it. Alright, 4.1, how do reactions occur? Key understandings and outcomes covered in this video. We need to be able to define the term rate of reaction. We need to talk about collision theory and how that impacts how a reaction occurs. We outline the requirements for a collision, for a successful collision to occur, and then we talk about this concept called equilibrium. Now, energy is the measure of ability to do work, and heat is a form of energy that could be released during a chemical reaction. By increasing the temperature of a reaction, we're giving the particles more energy, and we can say that the particles in that sample have a greater kinetic energy. The definition of kinetic energy is the energy of movement. So by heating something up, we're giving it more energy of movement. This graph down here shows you that in any sample, most of the particles will have an average kinetic energy about there, the peak of the curve. However, at any given temperature, there is a few particles that will be moving very, very fast. They have a lot of kinetic energy. But there'll also be a few particles that are moving very, very slowly. However, on average, most particles sit in the middle of those two extremes, and we would say that the average kinetic energy sits about there, or the tip of that diagram. If we change the temperature of a sample, we start to change the orientation of the graph. And what we can see is that at different temperatures, we still have some molecules that are traveling very slowly. We still have some that are traveling very, very quickly, but on average, what we've done is we've shifted those graphs to the right. On average, the kinetic energy has started to increase. So from 20 degrees to 40 degrees, you can see that the graph has moved to the right, and that means the average kinetic energy of the particles has increased because kinetic energy is on the x-axis. And that's generally true. As we increase the temperature of a sample, we increase the speed of movement, which makes those particles move faster. They have more energy and they have more ability to do work. Now, a chemical reaction could either occur very quickly or very slowly depending upon a number of factors. And for a chemical reaction to occur, certain criteria need to be met. The reactants need to have a certain amount of kinetic energy. They must be moving at a certain speed. That's because they need to break the bonds in the reactants, and we call that an energy barrier. The second criteria is that those reactants must be in the correct state. And the third and one of the most important criteria is that they must collide in the correct orientation. Now, a fast reaction, that's something that happens in a blink of an eye. So an airbag is an example of a very fast reaction. A very slow chemical reaction could be something like rusting, which takes many years to occur. So when we discuss orientation, we want to think of this as like a probability kind of model. That whenever these molecules collide, there's the chance of a successful collision. But they need to collide in a very specific orientation for that reaction to occur. In those four images, only one of those particular reactions has the right orientation. The other three will simply collide and then bounce off each other to undergo another collision. So that means that most collisions between reactants actually don't result in a reaction. Most of them are unsuccessful, and then they'll move off and continue colliding with other reactant molecules until a successful collision occurs. The job of engineers is to try and find ways to increase the chance or the probability of a successful reaction occurring. Now, when reactions occur, we want to measure how fast they occur. So we measure these reactions by their rate, the rate of reaction. And the rate of reaction is defined as the change in amount of products or the loss of reactants per unit time. So, and the amount of reactants may be measured in grams, it could be a concentration, or it could be a volume if we're talking about a gas. And then time is generally measured in seconds. So we have a formula where we have the amount of a reactant at one time, take away the amount of reactant at another time, divided by the change in time will give us our rate of reaction. So if we're measuring something in grams and we're timing something in seconds, then our units of rate of reaction would be grams per second. How the change in grams is occurring per second. If it's a faster rate, it will have a higher change. A smaller rate, a lower change. If we're measuring a volume, volumes can be measured in mils. So the rate might be mils of gas produced per second. If we're measuring concentration, a change in concentration, then again, we'd be looking at the change in concentration, which is given the symbol big M. Big M stands for concentration. Change in concentration per second would be ms to the minus 1. Some reactions that we'll come across are represented with these double-headed or equilibrium arrows. These indicate that the reaction may proceed either in the forward direction or in the reverse direction. Ammonia is prepared from nitrogen and hydrogen, and it is an example of an equilibrium reaction. And what happens in an equilibrium reaction is there is a balance between reactants and products. But if we were asked to describe the forward reaction would be written left to right. So nitrogen plus hydrogen goes to ammonia. If we were asked to describe the reverse reaction, we would be looking at the breakdown of ammonia into its elements, nitrogen and hydrogen. So that is an example of an equilibrium process. Thanks for watching, guys. Don't forget, drop a like on the video, subscribe if you're new. See you